Hello everyone, welcome back to Power System, class number 13. In this class, we're going to talk about long length transmission line. So in the medium length transmission line or even short length transmission line, we lumped all the parameters together for the whole length. So you can only have two quantity available for you. It's basically sending end quantity and the receiving end quantity. You can find VS or VR, but you cannot find any quantity in between the line because you lumped all the parameters together. So that is okay for short and medium line length because this line length is not that big, that long. So you can go with the two end parameters. But if your line length is like really long, like say 500 kilometers, 1,000 kilometers, then you need to have the ability to find the line parameters at any distance you want. That is the long line model, which is basically called distributed parameter model. To do that, again, we're gonna use the same kind of pi model here, as you can see. So we have receiving end and sending end, receiving end here, sending end over here. So we have a section of line from x distance of the receiving end, and that line length, the section of the line we have here is delta x. And the whole line length is L, as you can see over here, right? So looking at a small section from the x distance from the receiving end. And over here, your z, small letter z here is r plus j omega L. So what is r here? R is resistance value ohms per kilometer, or right? Then you have L is Henry per kilometer. Then you have your G is 0 because we are assuming there is no current conduction between line or line to neutral. So conductance is 0. And your C is also Farad per kilometer, right? So these are the unit here. And this is 0. So then small z and small y, those are impedance and admittance per unit length, which is kilometer, okay? So let's see how can we model this. To model this, if we model that section of the line, that will come to a second order differential equations, okay? Your book has a detailed derivation of the model. I'm not going to spend time on it. Please review the model book for the derivations. And over here, your gamma is basically square root of z and y. That comes to alpha plus j beta. So what is alpha? Alpha is called attenuation constant. All right, that means how your signal is attenuating over the line that will given by the alpha. That means if you look at the attenuation over here, you can, if your attenuation could give you the how your signal declining over the length, right? So that is your alpha, right? And beta, what is beta? Beta is called phase constant. What that means that how your phase is changing with the distance of the line from your reference. So that is your radian per meter or kilometer. Over here is per kilometer. And alpha is dB, is magnitude per kilometer. That's the unit for alpha and beta, all right? So this is alpha, this beta over here is not same as your phase difference between current and voltage or angle difference between your bus voltage. This goes to the wave nature of the your signal, and that is basically giving you, in terms of wave velocity, is giving you what is the angle difference your wave at any point at a constant time from the reference, all right? So the solution for this one, proposed solution is A1 exponential gamma x plus A2 exponential negative gamma x. And if we do that math, over here, you will come down to these two solutions over here, A1 and two value. So now there's one quantity you have to mention here is GC. It's called characteristics impedance. We're going to talk about that more in next class. It's important parameter for the transmission line. We're going to talk about it in the next class. So with that, now you have your Vx equation here and Ix equation over here. If you go further to simplify that, you'll get equation for Vx and Ix. What does it mean here? Now you can look at here, two equations, voltage and current can be determined at any point of the line, because x could be any point of the line. So x is right here, it could be right here, it could be right here, it could be right here. Any point of the line, you can determine the voltage and current, right? So this is your A right here, if you look at that. And this whole thing over here is your B right here. And this whole thing over here is your C. And this thing over here is D, and D is always equal to A. So these are the A, B, C, D value for the line. Now you can find the voltage and current at any point you want from the receiving end, because we're measuring the distance from the receiving end. Why from the receiving end? Normally receiving end quantity, your voltage and the current is given because you're supplying a load, and you have a constant voltage at the load, because load needs a constant voltage, and your current depends on the load. So that's why we measure from the receiving end. Then if you go back here, this over here, this can be also, all of them can be also expressed in hyperbolic function. So that's your cosine hyperbolic gamma x, and GC sine hyperbolic gamma x. So this is also again in hyperbolic function. So that is again this over here, this is your A, this whole thing over here is your B, and this whole thing over here is your C, this whole thing over here is your D. Again, A equal to D, right? So now if you go all the way to the sending end, so you can find, if you now replace, just simply replace X with L, you can go all the way to the end of the line, which is sending end, you can find the sending end voltage. Again, this is your A again, this is your B again here, and this is your C here, and this is your D, right? So that is a long line model. The long line model has the advantage that you're taking one small section at a time and modeling it, so you can have the parameter at any point of the line. All right. So again, you have see that A is this, B is C is this, and also in exponential form, you have A is exponential gamma x plus exponential negative gamma x over 2. That's also equal to D, and B is GC exponential gamma x negative exponential negative gamma x over 2, and your C is 1 over GC time exponential gamma x negative exponential negative gamma x over 2, and over GC again is square root of Z over Y, right? Small z over Y. All right. So that is the model for ABCD constant. If you know ABCD constant, you can find voltage and current. So pi model for the long line model. So we're defining prime over here to distinguish from your medium line model. And you know that if you have this, you have this equation over here. So if you have a short circuit test, that means you can make the short circuit over here. So VR would be 0, right? If your VR is 0 over here, that means your this one becomes GC if you compare it to the pi model. So your G prime becomes GC sine hyperbolic gamma L. So that's a short circuit. And open circuit test, if you leave it open now, so your VS over here is a VR, right? Your VR plus whatever loss over here is GL. And also for open circuit test, your IR is 0. If IR is 0, your IL over here, this IR is 0. So then, now if you combine these two equation here, you can find VS over VR. That is to be right here, and that also equal to this one here. This is your basically A. If you look at this, basically your A in your pi model, right? So what would be the what would be your y prime over 2? Y prime over 2, but you can find from this equation over here, y prime over 2 would be cosine hyperbolic gamma L negative 1 over g prime. That your y prime over 2. Now, if you do some manipulation with the trigonometry, that will come down to this equation over here. So that's your y prime over 2, and g prime is gc sine hyperbolic gamma L. Also can be written as this one by using this manipulation over here. So these are the two parameter on your line, g prime and y prime over 2. If we have them, then you can just basically go ahead and find A, B, C, D constant in terms of pi model now. So this is your A over here, this is your B over here. So this is your A, this is your B, and this is your C, this is your D. Again, A equal to D, and as you know that your G prime and Y prime by 2 is given by these two equation over here. So with that, you can model your parameter in terms of A, B, C, D model with the Y prime by 2 and G prime. And if you for a medium line, your lambda is J beta, and also for the gamma sine hyperbolic gamma L is gamma L. Then if you do that, your y prime by 2, it becomes y by 2, g prime becomes c. That's you can go back to the medium line from your long line model. Honestly, if you have a long line model, you can use it for any model, and you get more accurate results. We're going to do some problem solving in the class to show you that. So this is the comparison over here. Your short circuit line, you have seen all of them. This is the medium line, and this is your long line model, and all follows the same matrix right here, right? Then we're going to do this problem in the class to give you more insight to the line modeling, and we'll see you in next class.